Welcome, fellow travelers of the cosmos, to a journey through time and space. We stand at the precipice of the ultimate frontier, gazing back billions of years. Our vessel? The Big Bang Theory, explaining the birth and evolution of everything we observe. Prepare yourself, as we'll be navigating through realms of extreme density and unimaginable temperatures. Fasten your intellectual seatbelts, as this exploration will be nothing short of extraordinary. Let the journey begin. Imagine, if you will, a time before time, a realm where our current understanding of physics collapses upon itself. This is the domain of the singularity, an infinitesimal point containing all the matter and energy that would become our universe. In this crucible of cosmic creation, gravity, density, and temperature reach unimaginable extremes, defying our ability to describe them with conventional laws of physics. The very notions of space and time as we know them become meaningless. It's a concept that stretches the limits of human comprehension, a realm where our equations break down and our intuition falters. Yet from this point of seeming nothingness, our universe was born. The singularity is a stark reminder that the cosmos holds profound mysteries, secrets waiting to be unlocked. It's a humbling reminder of the vastness of the unknown and the incredible journey that lies ahead. It's difficult, if not impossible, to truly grasp the conditions of the singularity. Imagine all the stars, all the galaxies, all the matter and energy we observe today compressed into a volume smaller than a single atom. The laws of physics, as we understand them, simply cannot cope with such extremes. It's a realm where quantum mechanics and general relativity, the two pillars of modern physics, collide. But even though we may never fully comprehend the singularity, we can explore its implications. It's a testament to the universe's capacity for extremes, for packing unimaginable energy and potential into the smallest of spaces. The singularity represents the ultimate paradox, the beginning of everything we know, arising from a point that seemingly had nothing at all. It's a concept that continues to fascinate and challenge physicists and cosmologists to this day. From this point of infinite density, the universe exploded into existence in a fiery maelstrom of energy and expansion. In an incomprehensibly small fraction of a second, the universe underwent cosmic inflation. Picture space itself stretching and expanding faster than the speed of light. The universe ballooned in size, smoothing out initial irregularities. This rapid expansion explains the uniformity of the universe and the formation of galaxies and stars. While the era of inflation lasted for a fleeting moment in cosmological terms, its fingerprints are etched into the very fabric of our universe. We see evidence of this rapid expansion in the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation, discovered in 1965, provides a snapshot of the universe when it was just 380,000 years old. It reveals subtle temperature fluctuations, tiny variations in the otherwise uniform cosmic background. These fluctuations, though incredibly small, represent the seeds of galaxies and galaxy clusters, regions of slightly higher density that would eventually collapse under their own gravity. The cosmic microwave background radiation offers a direct link to the era of inflation, providing compelling evidence for this extraordinary period of expansion and offering a glimpse into the universe's earliest moments. The universe, moments after its birth, was a hot, dense soup of energy. But like a good cup of coffee on a cold morning, it began to cool. As the universe expanded, it stretched, and as it stretched, it cooled. This cooling was crucial, for it allowed the universe to transition from a chaotic state to one where order could emerge. Imagine a blacksmith plunging a red-hot horseshoe into cold water. The sudden cooling tempers the metal, making it stronger, more resilient. Similarly, the cooling of the universe tempered its very fabric. allowing the fundamental forces that govern the cosmos to crystallize. Before this cooling, the forces of nature were unified, indistinguishable from one another. But as the universe cooled below a critical temperature, this unified force began to break apart, much like a prism splitting white light into its constituent colors. First to emerge was gravity, the force that draws massive objects together. It holds us to the Earth and the Earth in orbit around the Sun. Next came the strong and weak nuclear forces. They govern interactions within atoms. Finally, electromagnetism governs interactions between charged particles. It's responsible for light, electricity, and magnetism. These forces set the stage for the creation of matter. The universe continued to cool, setting the stage for another dramatic transformation. Now, a few minutes old, it had cooled to 1 trillion degrees, still hot, but cool enough for something extraordinary. The universe was teeming with quarks, the building blocks of protons and neutrons. Quarks combined to form protons and neutrons, driven by the strong nuclear force. These particles, the building blocks of atomic nuclei, were now abundant in the young universe. The universe, now populated with protons and neutrons, was ready for the next act in its grand evolution. This process, known as Big Bang nucleosynthesis, is a cornerstone of our understanding. The universe was still incredibly hot and dense, perfect for nuclear fusion. Protons and neutrons fused together, releasing tremendous energy. First, they formed deuterium, a heavy isotope of hydrogen. These nuclei eventually formed helium-4, the second most abundant element. Hydrogen, helium, and trace amounts of lithium and beryllium emerged, setting the stage for the cosmos. The universe, now approximately 380,000 years old, was still a vastly different place than the cosmos we know today. It was a hot, dense soup of protons, electrons, and photons, all constantly colliding and interacting in a chaotic dance. Imagine a crowded dance floor, with dancers constantly bumping into each other, unable to move freely. This is what the early universe was like, a cosmic mosh pit of particles and light. The photons, the particles that make up light, were constantly being scattered by free electrons, unable to travel any significant distance. This constant scattering of photons meant that the universe was opaque, like a dense fog. Light couldn't travel freely, and the universe was a brilliant but blurry sea of light and matter. The universe, like a cooling ember, continued to cool. With this cooling came a profound change, as significant as the formation of the first atoms. The universe was about to become transparent. As the temperature dropped, the energy of the photons diminished. Electrons were captured by protons, forming the first neutral hydrogen atoms. The fog began to lift. Photons traveled unimpeded across the cosmos. The universe became transparent. The universe, moments after the Big Bang, was a rather homogeneous soup of particles, but the universe, as we know, thrives on complexity. And that complexity, my friends, is born from structure. From the seemingly uniform distribution of matter, gravity, the architect of the cosmos, began to exert its subtle influence. Minute differences in density, tiny quantum fluctuations, amplified by the universe's rapid expansion, became seeds of change. These denser regions, pockets of slightly stronger gravitational pull, started to draw in the surrounding matter. Like cosmic vacuum cleaners, they swept up atoms of hydrogen and helium, growing larger and denser over eons. This process, a cosmic ballet of attraction and accumulation, set the stage for the emergence of the universe's grand structures, the majestic galaxies and the glittering stars within them. About 200 million years after the Big Bang, the first stars were born. These giants, mostly hydrogen and helium, were far larger and hotter than our Sun. In their cores, nuclear fusion ignited, hydrogen fused into helium, releasing energy that lit up the universe. These stars burned bright and fast, exhausting their fuel in a few million years. Their deaths seeded the cosmos with life-essential elements. Supernovae scattered carbon, oxygen, and nitrogen into space. These elements became the building blocks for planets and life. The universe, now adorned with the light of a billion suns, continued its relentless evolution. The relentless pull of gravity drew stars together, forming vast collections bound by their mutual attraction, galaxies. These galaxies, islands of stars and gas, were not static entities. They swirled and danced, drawn together by gravity's invisible hand. Some galaxies, like our own Milky Way, assumed graceful spiral shapes, their arms adorned with newborn stars. Others, through collisions and mergers, evolved into elliptical giants, their stellar populations ancient and serene. The universe was no longer a uniform sea of particles, but a tapestry woven with threads of light, a cosmic web of galaxies stretching across unimaginable distances. This process of galactic assembly continues to this very day, a testament to the dynamic and ever-changing nature of the universe we inhabit. For centuries, we humans believed in a static, unchanging cosmos. Then, in the 20th century, we discovered the universe's expansion. But the universe, it seems, had one more surprise in store for us. Observations of distant supernovae, those cosmic beacons that mark the end of a star's life, revealed something astonishing. The expansion of the universe is not slowing down as gravity would dictate, but accelerating. This discovery sent shockwaves through the scientific community. What unseen force could be counteracting gravity's pull, driving the galaxies apart at an ever-increasing rate? The answer, it seems, lies in a mysterious entity we call dark energy. Dark energy, a pervasive force that makes up about 70% of the universe's total energy density, acts as a sort of anti-gravity, pushing everything apart. Its exact nature remains one of the greatest mysteries in modern cosmology. The Big Bang theory is supported by a wealth of observational evidence. The cosmic microwave background radiation is a faint afterglow of the Big Bang. Discovered in 1965, it permeates the universe in all directions. It's a snapshot of the universe at 380,000 years old. These tiny temperature fluctuations are crucial. They represent the seeds of the large-scale structure we see today. Distant galaxies are moving away from us. Astronomer Edwin Hubble discovered this in the 1920s. He observed that light from distant galaxies is red-shifted. This red shift is like the Doppler effect with sound waves. The farther a galaxy, the faster it recedes. Hubble's law shows the universe is expanding. The Big Bang theory is a living, breathing framework, constantly being refined by researchers. They chart the vast cosmic ocean, seeking to understand the universe's deepest secrets. Dark matter, an invisible substance, makes up the bulk of the universe's mass. Another mystery is the ever-accelerating expansion of the universe, driven by dark energy. These are just two frontiers being explored in cosmology today. The quest to understand the Big Bang is not merely academic, it has profound implications for our place in the cosmos. By studying the universe's origins, we gain insights into the fundamental laws of nature. The discovery of the cosmic microwave background radiation provided compelling evidence for the Big Bang, confirming that our universe had a beginning. It revealed temperature fluctuations in the early universe, the seeds from which galaxies would form. Studying distant galaxies allows us to rewind the cosmic clock, observing the universe as it was billions of years ago. This provides clues about the processes that shaped the universe. The Big Bang theory reminds us that we are all connected, forged from the same cosmic crucible. The atoms in our bodies were once part of the Big Bang, recycled through generations of stars. We are children of the cosmos. The Big Bang Theory stands as a testament to human curiosity and our pursuit of knowledge. From the initial singularity to the formation of galaxies, stars, and planets, it's a story that spans billions of years, supported by observational evidence. From the redshift of distant galaxies to the cosmic microwave background radiation. These observations provide compelling support for the expanding universe. But the story of the universe is far from over. New discoveries push the boundaries of our understanding. The universe is dynamic, ever-changing, full of wonder and mystery. The Big Bang Theory explains many cosmic phenomena, but it's not the end of the story. It's a foundation for future generations of scientists. As our tools and models improve, so will our understanding of the universe. The quest to understand the universe is a journey without end. Every answer leads to new questions and mysteries. The universe is an intricate tapestry of energy, matter, space, and time. We must remain open to new ideas and ways of thinking. The universe is vast, complex, and awe-inspiring. It's humbling and ultimately knowable. The Big Bang Theory shows the power of human intellect. The story continues to unfold, inviting us to explore and unravel its mysteries. And so we reach the end of our journey, a journey that has taken us from the universe's fiery birth to the formation of galaxies, stars, and planets. We've explored the vastness of space and the depths of time, contemplating the forces that shaped our cosmos. Thank you for joining us on this journey through the cosmos. If you enjoyed this video, please like, share, and subscribe for more fascinating explorations of our universe. Stay curious and keep looking up.